Okay, let's talk about multivariable limits. So, single variable calculus, gotta recall what this limit is referring to. So, in single variable calculus, this limit is basically saying, okay, our x value for a function, so let's say this is my function, our x value of this function is approaching some point, in this case, 0, on both sides. So, what does our y value approach? In this case, it would be, our y value would be whatever y value is associated with this point. All right, so as the x value gets closer and closer to some number, what is the y value approaching? But in multivariable calculus, there's more than one variable. Multivariable calculus, we're essentially analyzing the height of the function, which is given by f of x comma y. And we're seeing how does the height of the function, what does it approach as both the x and the y value approach a coordinate point. So here's an example. Let's say that we have our function f of x comma y is equal to xy. And for any xy point that you plug in, right, it's going to correspond with a z value, with an output value that's analogous to the height of the function. And you can see that as the x value and the y value approach this point right over here, which I labeled as 3, 1, as both the x value and the y value approach that point, well, the height of the function right over here, that's going to be approaching 3, which I highlighted here. All right, so you're asking yourself, what does the height of the function approach as the x and the y value approach a point? And these limits, multivariable limits, are weird because technically, if I go back to this function here, technically I can approach this point from any direction, right? So that's a little weird because sometimes there might be discontinuities, and discontinuity, you only see it if you approach it in a specific direction. But in all other directions, the limit looks like it exists, right? It looks like it gives the same height value every time. But then there could be one discontinuity where you go a specific direction and then you get a different value. And since the limits don't match up in all the directions, the limit is not going to exist, which is actually one thing that we're going to go over, right? How do you evaluate these limits? How do you actually see if they exist? And it involves polar coordinates. And the squeeze theorem comes back. All right. So properties of these limits, very, very similar to the properties of what you might have seen in regular calculus. So the limit of a sum or a difference. So if I have the limit as x comma y approaches a comma b of f of x plus or minus g of x comma y, well, that's just going to be equal to the limit of f approaching that point plus the limit of g approaching that point. Or it can be plus or minus. And then if you have a limit of like a constant multiplied by a limit, you could pull that constant out. So it's the constant multiplied by limit of that function. And all of these work assuming that these two limits exist, by the way. So just want to make that clear. You also have like the power. Actually, let's do the division one because we just did the multiplication one, right? If you have the limit of f divided by g, that's going to be equal to the limit of f divided by the limit of g, assuming that this limit is not equal to 0, right? Because it's in the denominator. And then we can have, the power rule, so or exponent rule, whatever, right? The limit as f is raised to some power n, well, that's going to be equal to the limit of f raised to that same power, n. Okay? So, I mean, you've seen these before. They still apply to multivariable functions. Let's get into some practice problems. First one, pretty easy. Let's just say we have limit as x comma y approaches 3, 2. And then our function that we're looking at is going to be x squared times y squared. So what is this going to be equal to? Well, this one, that's just direct substitution, right? Plug in 3, plug in 2. That's going to be 9 times 4, which is 36. And this is very nice because, well, this function right over here is continuous, right? This is like the polynomial function. And so no matter what x and what y value you plug in, your output is always going to be defined, right? So there's no restrictions on what x value and y value you can put in. When you start dividing by, x's and y's on the denominator, and you start to have this undefined stuff, that's when those, discontinuities can start to creep into the problems. All right, so I just want to make that clear. Man, I've been using the experimental version of Excalidraw and have this LaTeX support, so I can just enter in the LaTeX code and it gives me this nicely limit. All right, what is this limit? Draw for yourself. This one, also direct substitution. All right, plug in 0, plug in 0. 0 is on the numerator. This limit is just 0. Now we're going to be moving on to other techniques. All right, so when direct substitution doesn't work, like you see here, because the denominator is going to be 0, and we substitute in 0, 0 here, then you have to use other methods, and these methods, you've seen them before, factoring, conjugate, all of that. So how do you think we can evaluate this one? Well, is there any way to factor out the numerator? Yes, that's a difference of squares. So this is going to be the limit. Too lazy to put that every time, but this is going to be x minus y times x plus y because it's a difference of the squares. And this x minus y cancels out with the x minus y on the denominator. So this is just the limit as x plus y approaches, and then when you substitute in this 0, 0, right, because x and y both approach 0, so if you just have x plus y, that's just going to approach 0 when you substitute it in. All right. It's important to keep in mind that the limit, the point doesn't have to always be defined. Like if we're looking in single variable calculus, right, you could have a hole in a graph where, the point isn't defined there, but the limit can still exist. Right? As you approach the x value, you're getting really, really close to the value here. It doesn't matter that it's undefined. You only care about, the y value when it's extremely close to that point. All right. And it's the same thing for multivariable limits. You don't care if the function is actually undefined at that specific 0, 0 point. You only care what is the value approaching near that point. Next problem. How can we do this one? Well, it's also approaching 0, 0. This is going to be the limit. And once again, we're going to look to see if it's undefined first. So yeah, it's undefined. So we can factor out the numerator. We can factor in the numerator. Both these terms got an x in common. Why not factor it out, cancel with the denominator, plug the point in, that's just a 0. All right, I hope you're starting to notice a little trend here. How would you do this one? So for this one, notice how there's like a thing minus another thing, right? And so that's like a pretty big hint that this is going to be conjugate method. So you're going to have to multiply by the conjugate. Also, since it deals with like square roots and, just plugging it in direct substitution, that doesn't work at all, right? So you got to do this using the conjugate method. Very quick. This is going to be limit and then x squared plus y squared minus x divided by y squared. And you're going to multiply the numerator and the denominator by all of this right over here. Except it's going to be plus x. So I'll just do that. So now what is this going to be equal to? Well, I can distribute these. So let's simplify the numerator first. So this is going to be a difference of squares. So this is going to be x squared plus y squared. And then all that cancels out and you have minus x squared. Ooh, nice. The numerator is just y squared. And then on the denominator, right over here, you have y squared multiplied by all this. And what do you look at that? The y squares cancel out, Very, very nice. Just plug everything in. So you have 1 over the square root of x squared plus y squared plus x. And it approaches 0, 0. So if the x value and the y value, they both approach 0, man, the denominator, that's just going to be equal to 0. This limit does not exist. Okay? If the limit was approaching another number like 1, 2 or something, then you would be good. All right? Just be careful with, sometimes you may use these methods, but, just the overall values of the limit, the overall values that it approaches still can make this undefined. Here's where multivariable limits kind of take a turn, and it starts getting pretty hard from here, because now this is going to be some pretty new stuff. So looking at this limit, it looks like there's no clear way of going on with this. And this is the method, you got to use a method where I was talking about before. So remember how, like, if you want to take a limit, or you want to find out if the limit exists at a specific point, you can approach that point from different directions and see if all those limits match up. And if the limits don't match up, then you know that it doesn't exist. All right. So you can improve that, you can show that this limit does not exist if the limit approaching from different directions is not given the same value. So if you approach the same point, but the height of the function is not the value, is not the same value, then the limit doesn't exist. So what we can do is we can approach this when x is going to 0. So what do I mean by that? Well, if you look at this function right over here, right? Let's say you wanted to find out what the limit is when x and y, when both the x value and the y value approach 0. So one thing I can do is I can just approach it from the line y is equal to 0, right? I can just set the y value equal to 0 and just alter the x value so that it just approaches just like a straight line towards the center. Or I can set the x value to be a constant, like the x value to be 0, right? X is equal to 0, and I just let the y value approach 0, like that. All right, or I can approach along the line y is equal to x. So I can approach along the line y is equal to x, or y is equal to negative x, right? So these are all the different ways, or not all the different ways, but just some ways that you can approach a function, right, to try and see if the limit does not exist. And the reason why you use those specific methods, so you can approach along y is equal to 0, x is equal to 0, y is equal to x, y is equal to negative x. The reason why you use these main methods is because they're simple, right? If you're approaching along, in this case, x is equal to 0, well then all you have to do is just substitute all the x values here with 0. Or if you're approaching along y is equal to 0, just substitute all the values here, right? It's really easy to deal with. So let's approach along the line x is equal to 0. So this is going to become the limit as just y approaches 0 now, because we know that x is already 0, right? We're approaching along the x-axis. We substitute x is equal to 0 in for all of this. So this is just going to be negative y squared over y squared. And then the y squareds cancel out. So you get just negative 1. All right, so this is the first value that we got. Now we got to try out other values. All right. Now I want to make something really clear, and I said this before, I'm gonna say it again, okay? So when you're approaching from, y is equal to 0 or x is equal to 0, right? And let's say that all those values magically just equal to each other. That does not mean that the limit exists, because theoretically, there's infinitely many directions that you can approach a single value when you're in the xy plane, right? You can approach it from this way. You can approach it from, I don't know, y is equal to x squared or something like that, right? You can approach it infinitely many ways. And so there's actually specific methods that we'll use, like polar coordinates, squeeze theorem, right, that actually guarantee that the limit exists or does not exist. So let's approach along y is equal to 0 now. So this is going to be the limit as x approaches 0 now, because we held the y value constant. And when we plug in y is equal to 0 into here, we just get x squared over x squared. That's just going to be equal to 1. And of course, this value, the limit for this value here of 1 is not the same as the limit approaching along x is equal to 0. And so the limit does not exist. You see, this is just a method to see if the limit does not exist, but does not guarantee that the limit does exist if the values were equal to each other. So if I were to summarize this method, right, I would call this the pathway method. And this pathway method checks if the limit even exists. So if you approach this, if you approach 0, 0 from x is equal to 0 or y is equal to 0, or you approach it from all these different directions, and you see how, and you notice that, so you approach this coordinate from all these different directions, and you notice that not all of them are equal to each other, that means that the limit does not exist. So if the values aren't equal, the limit does not exist, because it approaches different points as you approach 0, 0. All right, but if all of these limits, they do approach a single value, then you have to do more investigation. Because theoretically, there's infinitely many values that you can use to, or infinitely many different ways you can use to approach 0, 0, right? So you would have to do more investigation, other methods we'll discuss later, to find out if the limit exists. So mainly, this pathway method is to check if the limit does not exist. Very easy way. All right. So let's take a look at this one. We're going to use the same strategy. Let's approach this from x is equal to 0. So when x is equal to 0, you have the limit as x, y approaches 0, 0. And when x is equal to 0, this is just going to be 0 divided by y squared. This is the limit as y approaches, this is the limit as y approaches 0, because we held the x value constant, right? We keep the x value constant, so the only thing we're changing is our y values approaching 0 now. And so the limit as the y value approaches 0 of 0 divided by y squared, that's undefined. So the limit, undefined, you get 0, 0. The limit here does not exist. Let's take a look at this limit. Okay, let's just do it. Let's approach this from y is equal to 0 first. This is going to be the limit as, so now we keep our y value constant. So the thing that we're actually varying now is we're getting closer in the x direction, right? So this is the limit as x approaches 0 now of, and when our y value is equal to 0, this is just going to be equal to 0 divided by x squared, which just gives us 0 over 0 indeterminate form. This doesn't really give us any information. Okay. Let's try y is equal to x. Let's approach along the line y is equal to x. So, on the xy coordinate plane, right, you got 0, 0. Let's approach it along y is equal to x. All right. So this is going to be the limit as, so what do we want to do? Well, let's just substitute in all the x's for y's, right? Since we're approaching along the line y is equal to x, let's just substitute y in everywhere we see x. So this is going to be the limit as y approaches 0 of y squared divided by, and this right over here is y squared plus y squared, or 2y squared. Y squareds cancel out, so you get 1/2. Let's do another value. Let's try this along. Okay, so when we tried it along y is equal to x, it gave us 1/2. Let's try this along y is equal to negative x. All right. So this is going to be the limit. And this time I'll do this a little bit differently. So everywhere I see a y now, I'm just going to replace it with a negative x. So this is going to be, if I plug in negative x into here, I get negative x squared. If I plug in negative x here, I just get x squared. So this is 2x squared on the denominator. And this is going to be the limit as x approaches 0 now. Right, because we substitute in y in for x. So now the y is gone, but we still have, or we're approaching now in the x direction, right? Looking at x approaches 0. X squared cancels out. Negative 1/2. Oh, wait. those two things are different from each other. Therefore, the limit does not exist. Because when you approach it different ways, it gives you different values. If it helps for organization, maybe you can make like a table. You can do like approach on one side. So this is approach. And the other side would be the value that you get when you approach it from that direction. So for example, let's say that we approach from y is equal to x. Let's see what happens. All right, so everywhere we see, we can do either way, right? We can substitute in y here, right? So it's y to the third, y squared, or we can substitute in x into this part, right? Either way, get the same answer. This is the limit as x. So let's do the substitution with x. So everywhere we see a y, we just substitute that with the x. So this is going to be x to the third power divided by x squared plus x squared, which is just 2x squared, is the limit as x approaches 0. This cancels out, and you just get x over 2. The limit as x approaches 0 of x over 2 is just 0. Let's approach this from y is equal to 0. So if we do the limit, so if we let y is equal to 0, that's just x to the third over x squared is the limit as x approaches 0. So that cancels out. So that's just going to give you 0. Let's do y is equal to negative x. So this is going to be the limit. And this time, let's just make things simple. Everywhere we see everywhere we see a y, we just substitute in negative x here. And it looks like it just yields the same result. Okay. Let's do something creative. So if we're approaching 0, 0, I mean, technically, we can approach it as long as we have a curve that passes through the point 0, 0. Like, for example, if this was the limit as x, y approached, let's say if instead of 0, 0, this was 1, 2, for example, which is this point right over here. This is 1, 2. What I can do is any curve, it could be a quadratic, it could be a straight line, any curve that passes through the point, right? So this is y is equal to 2, this is x is equal to 1. Any curve that passes through the point, I can use as a way to approach the point, right? So let's do x squared. Let's just be a little fancy. Y is equal to x squared. Because x squared passes through the point 0, 0. So everywhere I see a y, I substitute in x squared, and I get the limit as x approaches 0 of x to the third power divided by x squared plus x to the fourth power. If this was x approaching infinity, then the highest power would dominate, and this would look something like 1 over x, right? You'd have like a 1 over x scenario, because you would pick x to the third power and x to the fourth power. But since this is approaching 0, the lowest power actually dominates. Think about it. When x is a really small number, like 0.001, when you raise 0.001 to the fourth power, that gives you a number that's really close to 0. But if you only do it to the second power, that gives you a much higher number. And so it's actually going to be the x squared term that controls the value of, the overall value of the denominator. The x to the fourth is negligible. So this is actually, you're going to pick lowest power on numerator and lowest power on the denominator as the main contributors to the value. And so this is just going to give you x, right? X to the third divided by x squared is x. And the limit as x approaches 0 is just 0. Now, there's a problem. Pathfinding way doesn't work. And that's where we need to use different methods. Let's get into the polar coordinate method. Polar coordinates, very commonly used when you see this 0, 0 here. So when both the x and the y value approach 0, big clue that you gotta use polar coordinates. Now you can actually use polar coordinates for when it's not approaching 0, 0, but you first gotta understand, the case of 0, 0. All right, that's very common. So recall that x is equal to r cosine theta, and y is equal to r sine of theta. This just comes from the fact that, right, normally you have a point, normally you have a point x comma y, but in polar coordinates, you're trying to represent x comma y. So this is your original x comma y. But in polar coordinates, you're representing this using the angle it forms with the x-axis. This is theta, and the distance from the origin, or the r, kind of the radius. And notice how x squared plus y squared gives you r squared. So that's another property. X squared plus y squared is equal to r squared, because that's a right triangle. These are 3 things you gotta know. Let's just substitute everything in here. All right. So this is going to be the limit. Now, think about it. If I'm approaching the origin, right? Let's say I'm going from this point and I'm going to this point, right? So I'm going from here to here. Notice how my r value, my radius or my distance from the origin, notice how it's getting smaller and smaller. That distance is getting smaller and smaller until, it actually, infinitely reaches the origin, infinitely gets close to the origin. So this is going to be the limit as our radius approaches 0, the r value approaches 0, because we're getting closer and closer to the origin, right? That's literally what this limit is describing. This is going to be the limit as r approaches 0 of, well, x to the 3rd power. Let me just cube everything here and substitute that in. So this is r cubed cosine theta cubed divided by x squared plus y squared, r squared. Cancels out. You get r squared cosine of 3 theta. Or sorry, r cosine of theta to the 3rd power. Okay? This is the limit as r approaches 0 of cosine to the 3rd power theta. And what is this limit equal to? Well, as r approaches 0, the whole thing is equal to 0. So, yeah, it's just 0. All right? Now you might be saying, well, Ryan, we only did the limit as r approaches 0. But what about this theta part, right? Because we could be approaching 0 from many different angles, right? Imagine I have this theta right over here, this angle. I can approach 0, 0. I can approach the r value of 0, right? I get closer to the origin through this angle. I can get closer and closer to the origin through this angle, right? Doesn't this angle matter? It actually doesn't. That's what's nice about polar coordinates. You can approach the origin from any angle, but at the end of the day, you're still approaching the origin, right? You're still going to end up at the same point. It doesn't matter. All right. Now, the real reason, if you want to think about this algebraically, so that was kind of like the visual interpretation, right? Anywhere, any angle you go, you approach the same point. But algebraically, this actually used the squeeze theorem. So cosine of theta to the 3rd power, that's going to be in between 1 and -1, right? Because cosine of 0, that's equal to 1, and 1 to the 3rd power is just 1. And if you have cosine of 180 degrees or cosine of pi, well, cosine of pi is equal to -1. So -1 to the 3rd power is just -1. Now let's multiply everything by r. The reason why I multiply by r is because I want cosine of this to look like this with the r, right? I just want to look like it. I just want those to look like each other. So now we have r's everywhere. And then the limit, if I take the limit as r approaches 0, well, this is equal to 0. This is equal to 0. By the squeeze theorem, this has to be equal to 0. All right? So that's how you do these types of problems. All right, all you have to do is just substitute it in here, and if it's very nice, 0, 0, you can use polar coordinates to solve this. So let's say that if we did not approach 0, 0, and instead the x and the y values, they approached 3, 4. Now we run into a problem when we try to do this limit. But it's not at 0, 0. Let's say we were trying to do this limit when x, y, that's approaching 3 and 4. Let's graph this out. So 3, 4 is right here. And notice how this is the same as essentially the limit. We're essentially finding out the limit as the radius of this, because this is just a 3, 4, 5 right triangle. So this is a 3, 4, 5 right triangle. This is the limit as r approaches 5. and this is going to be the r times cosine 3 theta that we were talking about before. So instead of r approaching 0, now it's approaching 5. Now the problem is with this is when we're approaching the origin, the angle didn't really matter. But when we're approaching a point, when we are approaching a point that is not the origin, the angle does matter. All right? Because this is a point with radius 5. This is a point that has a radius of 5. This is a point that has a radius of 5. In fact, anything on this circle, any point on this circle right over here has a radius of 5, right? I mean, that's literally a definition of a circle, right? Every one of these points has some constant radius. So all of these points you can potentially approach if you're taking limit as r approaches 5 and you're not careful with the angle that you're approaching from. So what do you do now? Right, so this angle right over here, you can actually find it by using arctangent of the y value over the x value. But I mean, then this turns into another double limit, and then we don't want to do that, right? Like, you don't want to do the limit as r approaches 5, and you also got the theta approaching whatever tan inverse of, that is just not what we want to do. So this is the perfect problem for this scenario. So instead of approaching the origin, now we approach 2, 1. All right. So how do I write out what x is equal to and what y is equal to in polar coordinates if we want to center around this coordinate? All right, I'll show you what that means. So normally, when we're trying to find the r value, we usually find the r value relative to the origin. But here, we want to measure the r value, the distance, and the angle. We want to measure everything relative to the point that we are approaching. All right, so we want to measure this r value relative to this point and not this point, the origin. So how do we do this? Well, so this is the point 2, 1, right? Imagine if I have a point 5. Now, the distance from 2 to 5 is 3. Right? So notice how all I have to do to get the distance in the x direction is the distance in the x direction is just x minus whatever value that you're centered on, right? So whatever x value is here, you just subtract it by that value. So right, in this case, 5, which is the x value here, minus 2 gives us the distance of 3 that we're looking for. Right? If this was like 6, for example, then this would be 6 minus 2. That would give us the distance of 4, which we want. And it's the same thing for the y value. What we do to the y value is we say, okay, the y value, the distance for the y value, right, if this was number 3, for example, right, to find this distance, what we do is we take this y value here and we just subtract it by 1 because it's relative to this point. So we subtract. Now we get this distance of 2. Next step. And so, like, let's say if I have, let me show you this. So let's say if I have a point at 3 or 5, 3. The distance in the x direction relative to this point is x minus 2. And the distance in the y direction relative to this point is y minus 1. And this is the radius that I'm looking for. So once again, if this is x minus 2, this is y minus 1, I can use the Pythagorean theorem. So x minus 2 squared plus y minus 1 squared is equal to r squared. So we're transforming the polar coordinate in a way where we're centered at this point so that when we're doing the limit in the polar coordinate world, it can be the limit as our r value approaches 0 because everything is relative to this point. We're measuring the r distance from this point. So if we're approaching this point on the polar coordinate world, it's going to be like we're approaching 0, right? Because we measure relative to this point. Okay. I know I said that many times, but I want you to get this idea clear. All right, it can be pretty weird to understand at first. All right, what about the other properties? So we said how x is equal to r cosine of theta originally, and y is equal to r sine of theta. But how do we do it here? Well, if we have this angle theta that we make, then sine of theta is going to be opposite over hypotenuse. So it's going to be opposite over hypotenuse. That's sine of theta. So sine of theta is going to be y minus 1, y minus 1 is equal to r sine of theta. So we have y minus 1 is equal to r sine of theta, and you might have seen the pattern. you might see the pattern. That means that x minus 2 is r cosine of theta. All right. Okay. Now, how can we do this? All right, so now that we have all these values right over here, now it's time to make the substitution. Now it's time to make the substitutions. So what's x minus 2? X minus 2 squared plus y minus 1 squared. What is that? That's just going to be r squared, right? So this is going to be the limit as, or let's just not write it yet. Let's just do r squared first. What's the denominator? That's the square root of r squared. And the square root of r squared is just r. Usually in Calc 3, you would take the r value, that distance right over here, right? It represents a distance. Usually you would take that as non-negative, so you have that. R's cancel out, and you just left with r. And because I'm measuring the distance relative to this point, right, this is going to be the limit as I approach the r value of 0, right? Because if I measured the distance relative to this point, and I'm getting closer and closer to that actual point, the distance is going to get smaller and smaller. R is approaching 0. And the limit as r approaches 0 of r is just 0. There we have it. That's the answer. So let's write this in general. So what do we see? What are we seeing from these formulas? It looks like that x is equal to r cosine of theta plus that. I'm just going to call this value a. All right, a represents the x limit, b represents the y limit. X is equal to r cosine of theta plus b, or sorry, plus a. Wrong letter. Y is equal to r cosine, or oh God, r sine of theta plus b. And it looks like, from looking from this formula that we saw here visually, it looks like x minus a squared plus y minus b squared is equal to r squared. How do we do this one? Well, you got to do a squeeze theorem. Sometimes you might do them with sines and cosines. That's usually a big hint that you would use the squeeze theorem, because sine and cosine are bounded between, so sine, cosine, they're between -1 and 1, right? And you can use that to set up the squeeze theorem. So in this example here, what we can do is we see how as x and y approach 0, right? This is approaching 1 over essentially like a really, really small number, and that's going to blow up to like infinity. So you're going to have sine of like 1,000,000, and then it just gets larger and larger and larger, right? The input for the sine function just gets larger and larger and larger. Now we know that sine of just a random thing, random angle, I know that's in between 1 and -1. So in this case, I know that no matter what my input is, I know that sine of, in this case, my angle would be 1 over square root of x squared plus y squared. Whatever this value is inside of the sine, I know it has to be in between -1 and 1. It doesn't matter what value they're approaching, right? It doesn't matter what value they are. It's going to be in between those. Now I'm going to multiply both sides by x squared plus y squared. So I'm going to get negative x squared plus y squared. And this is going to be less than or equal to x squared plus y squared times sine of 1 over x squared plus y squared. And then this is going to be less than or equal to x squared plus y squared. And so if we take the limit as all of these equal to 0, well, this limit is just 0 from direct substitution. This is also 0. So this limit right over here has to be equal to 0. That's the squeeze theorem right there. So this one, that's kind of scary. Let's convert it into polar. Polar is easier, right? And it's approaching 0, 0. Let's do that. So this is going to be, I know x squared plus y squared. I'm too lazy to write out the limit, so I'm just going to go limit. All right, so this is sine of r squared. And then I have x squared times y. That's just going to be evaluate out to r to the third power cosine squared theta times sine squared theta. And then on the denominator, we also have another x squared plus y squared. So it's r squared 2 to 3 over second power. That's just r to the third power. Nice. All right, let's do this. So we want to start off with these thetas right over here. And we know that cosine of theta squared times sine of theta, I know that has to be in between 1 and -1. And if I multiply everything by sine of r squared, and then, so let me just copy and paste everything. All right, yeah, paste, paste, paste. And I take the limit as this approaches 0. So I take the limit as this approaches 0. Then this, so r approaches 0. Then sine of 0, that's just going to be equal to 0. So that's 0, that's 0. That means that this has to be 0 as well. So this limit is 0. Okay?